Thank you. And thank you very much to the organizers for the invitation. I'm really happy to be here and to meet all of these, so many model theorists. So I will be presenting in this talk some results related to the existence of rational points on varieties, all obtained by working over Berkovich analytic curves through a technique known as patching. So as we'll see, valued fields and valuations over functional fields of curves will appear quite naturally here and will play a central role. So to be a bit more specific, since there are so many approaches nowadays to studying the existence of rational points on varieties, here I mean local global principles, the approach of local global principles. So let me start by telling you what I'm calling a local global principle. And let's call it an LGP from now on as well. So you've probably already seen one of the most famous local global principles, the so-called Hasse-Minkowski theorem, which states that, so it was proven about a century ago, and it states that if you take a quadratic form with rational coefficients, and while you want to study the zeros of this quadratic form, you take the polynomial equation q equals 0, then it has a solution over q if and only if it has solutions over all of the completions of q, so over R and the fields qp for p prime. And as it turns out, this simplifies considerably the problem of the beginning of determining whether this, when I say solution, I mean non-trivial, of course, of determining whether this polynomial equation has rational solutions. So we've transferred now the problem to these larger fields, which have a better structure, so we can more easily say things in this case. In fact, it turns out we can solve the problem by effective methods over these larger fields. So given how this equivalence was useful here, we became interested in the same kind of principle, but in a much more general and abstract setting. So this is what I'm calling a local global principle here. Let's say LGP. You take a field F, you take a family of larger fields, which I'm going to call overfields, meaning F is strictly contained in Fi, and what you want to do is study now polynomial equations, systems of polynomial equations defined over the field F. So let's take a variety X over F, an algebraic variety, and then a local global principle is a statement that says that X has an F rational point if and only if it has Fi rational points over all of these overfields. So just to clarify a bit, we don't want just any family of overfields, okay? The idea here, the philosophy is that we'd like to, just like in the Hasse-Minkowski theorem, get some overfields that have a better structure than that of F, so that we can study, well, we can study this side by instead studying the more easier right-hand side of the equivalence. And this equivalence, when it holds, is what I'm interested in particular in a geometric context. So what I mean by that is in a context where, let's say, the field, the data, comes from some geometric setup. So just the specific case we're going to be talking about today, I'm going to call it a geometric LGP, is one where the field F is the function field of a curve. So you take some nice curve defined over a field, and you take its function field F, and then you want to know when is the LGP true for varieties defined over F. What kind of overfields are you going to construct? Well, typically, you encounter several families of overfields in the literature. Typically, let me just say a bit vaguely at the moment, that they are constructed locally. Locally where? Well, it depends. Sometimes there are discrete completions of F. Sometimes they're constructed over some well-chosen model of the curve C. For me, for instance, they're going to be constructed locally over the Berkovich analytification of this curve. So we'll see this in a moment. And this sort of LGP has been receiving a lot of attention in the last 15 years or so, mostly due to the fact that in 2009, Harbader, Hartman, and Krashen introduced a new technique for the study of this kind of LGP known as algebraic patching. So I don't know if I'll be able to tell you about patching. We'll see how much time we have left. But essentially, this is a very algebraic version of this technique known as patching, which has been proven to be quite useful in several directions in questions of in arithmetic questions, for arithmetic questions, let's say. So via this algebraic patching, what they show is that, let me be a bit vague, and I'll write down a precise statement very soon, is that geometric LGP is sometimes true when the field K is completely discretely valued. And for them, the Fi are constructed locally over a model of the curve, right? So what I did, as it turns out, is that this patching technique, it can be extended to Berkovich curves. So patching can be extended to Berkovich curves. It can be developed over Berkovich analytic curves. And an important difference with the Harbader, Hartman, and Krashen case is that now patching in this Berkovich setting becomes quite geometric. So this is, let's call it a geometric version of patching. Geometric patching. And as an application, I managed to generalize the results of Harbader, Hartman, and Krashen on geometric LGPs. And to be precise, what I proved, let me write down a precise statement, and then we'll keep it here and come back to it several times for more explanations. So let's take K, I'm also fixing the notation, to be a field endowed with evaluation, with respect to which it's complete. So here I'm going to assume that Vk is non-trivial, rank 1. In fact, all of the valuations that we're going to see in this talk are going to be of rank 1. So we have this complete valued field. Remark, I'm not saying it's discrete. It doesn't have to be discrete. I'm just asking it to be non-trivial, and even non-trivial is not strictly necessary. I just would have to be a bit more careful with what I say if I would include this case. So K is a complete valued field, and then we're working, we said, over a curve. So let's take C over K to be a reasonable curve. I'm going to ask it to be normal, irreducible, projective, and for now it's just algebraic, okay? It's a typical curve. And let's take F. We said it would be its functional field, right? So this is our starting field F. What are the varieties that we're going to be able to consider with these patching techniques? Well, the hypotheses are the same that Harbader, Hartman, and Krashen need. They're the following. So you take a variety X defined over F it's going to be a homogeneous, I'm going to tell you what this means, homogeneous variety over what? Well, over some group defined over F, which I'm going to call G, which is a linear algebraic group, but not just that, it's also a rational variety. So what do these things mean? Well, first of all, homogeneity over a group. What it means is that G acts on X, but not only does it acts transitively. So we have some strong, let's say, the variety is somehow very symmetric. Okay? So G acts on X, and somehow it acts transitively. So this is a transitive action. So for instance, torsors would be an example of homogeneous varieties. And this is really not very surprising in this context, because typically the kind of varieties for which we can say more things on the local global principle are homogeneous varieties. So this is not very surprising. What is more restrictive than usual, than the classical cases, is this rationality hypothesis. So what does it mean? I recall that what it means for G to be a rational variety is that it's birationally equivalent to some Pn over F. And, well, why do we need this? Because it turns out that only under a condition that is very closely related to rational, to G being a rational variety, can we prove patching, be it here or here? Can we prove that patching holds? So this seems to be quite crucial. And then I can tell you that if F were to be algebraically closed, then all linear algebraic groups would be rational. However, this is not the case. It's a function field of a curve, so that it's not really going to be as nice as algebraically closed, meaning that you can construct non-rational linear algebraic groups. In fact, one can even find tori that are not rational. So they don't have to be so exotic. And just to give you an example, which you can think of when I talk about this X, it's again the case of quadratic forms. So if I were to take characteristic of K different from 2 and Q defined over F a quadratic form, if I call X the quadric defined by this, determined by this quadratic form, then it's going to be homogeneous over what is going to play the role of G is going to be the special orthogonal group associated to Q, and it turns out this is a rational variety. Oh, you also have to assume that the dimension of Q is different from 2, but this is not very restrictive. So basically all the local global principles that we're going to see apply to quadratic forms. So if you want, you can just ignore these homogeneity and rationality hypotheses and think of quadratic forms. Right, so I'll leave this there and continue with the statement. So we have, this is the context, and remark, everything is algebraic. I haven't mentioned Berkovich spaces at all for now. But where do they come into play? Well, first local global principle, I haven't said yet what the overfields are of my LGP, right? And this is where we're going to use Berkovich spaces. So the first one, let's call it LGPMC, is the following local global principle. X has an F rational point, which is what we're interested in, if and only if, and now I'm going to mention some of these Berkovich objects, this is true for a certain family of overfields indexed by the points of the analytification of C. So here, CAN is the Berkovich analytification of C. So it's like an analytic variety of dimension 1 over the field K. It makes sense that we have meromorphic functions defined on it. And these fields MC are just germs of meromorphic functions on C. So they're just meromorphic functions defined around in some neighborhood of the point C. Right, so I'll tell you, I'll draw some things very soon, and hopefully that will help a bit. But let me just tell you that this is a reasonable local global principle in the sense that, don't forget, we wanted to simplify the study of the F rational points by studying what happens over the overfields. And this is going to be true, the things are going to be simplified if the family of overfields satisfy better algebraic conditions, let's say, than the starting field F. And this is going to be the case for the overfields MC. But from here, one can actually prove an LGP, it's actually equivalent to this one, where the overfields now, for the overfields, we don't really need Berkovich spaces. So what we can do is take completions. So I'll leave the example here and continue with point 2, LGP val. What does it say? Well, it says that X has an F rational point if and only if it has rational points on certain completions of F. What are these completions? Well, with respect to V's, valuations on F, which are non-trivial, because otherwise anyway, non-trivial, rank 1, always here, and I also want, when I restrict to K, because K comes with a valuation, right? We took a complete valued field. So I want to take that into account. When I restrict to K, I'm either going to have the trivial norm on K. Anyway, I don't want to lose Zariski closed point, so I have to include those. So it's either trivial or it's just the norm we started with, the valuation we started with on K. So now here, the completions are, the overfields are these completions. We technically don't need Berkovich spaces to talk about them. And again, somehow they are larger and satisfy up to a certain point some better algebraic properties than the field F. So this all applies to quadratic forms. And now a natural question here, because remark, even if K were discretely valued, we would have here much more than only the discrete valuations on F. Much, much more, in fact. So a natural question here is, can one reduce to only those that are discrete when K is discrete? Because otherwise there's no hope. But can one reduce in that case to only V discrete? So this is a conjecture. So I'm writing on the other side because I'm also going to keep this. A conjecture of Kolyotelen, Parimal and Suresh, dating from 2009, where they say that if K is discretely valued, one can reduce to V discrete in LGP val. So, of course, I didn't mention it, but this theorem dates from like 2019. So when Kolyotelen, Parimal, and Suresh introduced the conjecture, they didn't do it in this Berkovich context. They even said it much more generally than this, but let's talk about it in this context. So it turns out the conjecture is quite difficult. There are some cases which are known, most of which obtained through case-by-case considerations. Known cases, for instance, quadratic forms. The case when G, so G, the group which acts on the variety, was defined over F. If it's defined over not only the smaller field K, but over its valuation ring, then that's fine as well, etc., etc. So now the question, which I'm hoping to talk about a bit today, is what can one say about this conjecture by working on the Berkovich curve CAN? Okay, so I was since part 1, the LGPMC, it's actually proved using this patching that I keep, this mysterious patching technique that I keep mentioning, which I said is geometric. So that means that most of the time, one can understand what's going on in this LGPMC by drawing stuff. So I'm gonna stop with LGPs for a moment and tell you, just recall some general things on Berkovich spaces. I was hoping that from Antoine's talk I could just say, well, you saw what it looks like, so let's just draw that. But that didn't happen, so let's take a moment and talk about Berkovich spaces for a little. All right, sorry. So let's say part 2, Berkovich, especially Berkovich analytic curves. That's all that we're going to need. So let's start with a complete ultrametric field. So it's a complete valued field. Again, V is rank 1. I'm not asking here V to be non-trivially valued. Berkovich's theory works over trivially valued fields as well. So what happens is that as a topological space, this field is totally disconnected. So it's a totally disconnected topological space. And what this means is that the connected components are points. So when it comes to matters such as defining analytic structures over K, and by that I mean like analytic functions or analytic varieties, then this is a bit problematic, because typically what you want from, let's say, an analytic function is to be able to say global stuff based on local data, right? An analytic function, you define it as being locally something which you write as a power series, a formal power series, which is convergent somewhere. So this is clearly going to be a big problem in the case of ultrametric fields, because, well, here the connected components are just points, so you have no hope of saying something more global other than on the point itself. So because of that, there have been several approaches to non-Archimedean analytic geometry, meaning to constructing a theory of analytic varieties that is a parallel to complex analytic varieties, but over these kinds of fields, over non-Archimedean fields K. Among these, which deal with this problem of totally disconnected. So one of the possible approaches to this is Berkovich's theory, in which Berkovich constructs Berkovich analytic spaces, where this problem is dealt with, and we do get something quite reasonable. So now these are analytic varieties over the field K, and in spite of this, if this big difference with C, with the complex numbers, these spaces, these analytic varieties, are analogous to complex analytic varieties. And they are reasonably nice in the sense that, while they're locally compact, they're locally path connected, And as in the complex case, one has an analytification functor. So a way to connect the algebraic and this analytic world. So analytification functor. What does this mean? Well, you take a scheme, a relatively reasonable scheme X, so locally a finite type is enough, and you can always associate to it a Berkovich analytic space called its Berkovich analytification. So essentially, you've taken an algebraic space, something given by algebraic equations over K, and you're looking at these algebraic equations analytically. And this can be seen as a Berkovich space, can be seen as a space in the category of Berkovich spaces over K. So there are also Gaga-type results, Gaga-type theorems for this analytification functor, meaning there are principles of comparison between, well, the let's say analytic version of the object and its algebraic counterpart. So an example of this would be, or let's just say remark, a proper analytic curve is always algebraic. Analytic in the Berkovich sense, I mean here. So what does that mean? That means that if I take a Berkovich space of dimension 1, which is proper, then I can always write it down as the analytification of some algebraic curve. So if we go back to the setting here, it means already that the curve C, I could have equivalently taken it to be analytic, satisfying the same properties of normally reducible and proper. I wouldn't have gained or lost anything. But then what about the field F? Well, this quite naturally brings us to meromorphic functions. Again, we're talking about analytic varieties. We have meromorphic functions on these varieties. And I'm going to denote with curly M the sheaf of meromorphic functions. So I'm not going to give an explicit definition here, but the definition is very close, if not almost identical to what happens, let's say if you've seen that for schemes or even in the analytic complex case. So in particular here, what happens is that if you take a reduced analytic space, I want to get to germs of meromorphic functions now because they appear in our LGP, and you take any x and y, what are the meromorphic functions around x, meaning functions which are meromorphic in some neighborhood of x? Well, it's just as usual. They're just going to be fractions of analytic functions. So it's frac of OX. And this, this sheaf actually satisfies a Gaga-type result, which is that in our case, for instance, if I were to take x over k to be a reduced proper curve, well, then I would have that the function field of x is the field of meromorphic functions, so now global meromorphic functions on the analytification of x. Basically, I'm saying that analytic functions on this analytic space, meromorphic functions on this analytic space, xn, are algebraic, essentially. So again, if we go back to our theorem and look at the setting, it means that I can just forget about the algebraic setting, or vice versa, if you want, the analytic, and just take a curve that is analytic, satisfies the same properties, and look at its meromorphic functions, global meromorphic functions. Okay? And these fields are nice, but maybe I'll tell you about that in some minutes when we go back to local global principles. So let's make the famous drawing. Example, the most typical example of a Berkovich analytic curve, the analytic affine line. Which is, of course, let me mention here, the analytification of the algebraic one. And one can draw it by using, well, you've probably already seen this, it's an infinitely branched tree. So this is what it looks like. And what can we say about A1? Well, it's quite nice as a topological space. It is locally compact. It is uniquely path connected. So what does this mean, uniquely path connected? Well, what it means is that if you take any 2 points, there exists a unique injective path connecting the 2 of them. And then one can find in A1 a copy of K. So these are the K points of A1. And where do we find them in the tree? Let's make this yellow. There are going to be some of the leaves of the tree, meaning there are going to be some of the extremities of the tree. In fact, more generally, one can find all of the Zariski closed points of the algebraic A1 in the analytic A1. And again, this was just a special case. The Zariski closed points are always extremities. I am, let's say yes, but I mean the trivially valued, it's still somehow infinitely branched. It looks something like this, okay? But I don't want to make the distinction anyway. We're not going to talk about trivially valued ones. So, but yes, a distinction should be made if you're really looking into details on A1. So since we're going to be talking about proper curves, projective curves, let me just tell you that from here one can construct P1. So it's a one-point compactification of A1. One obtains it by adding this infinity point. This is, by the way, again, a K point, the infinity point. So I've drawn it here for some reason, but let's say this is infinity. And then somewhere here, we're going to have 0 for a choice of coordinate. And one difference with the complex case here is that, well, the complex P1 is a sphere, whereas here you have a tree, something that is simply connected. So P1 is, of course, going to be compact. Again, is the analytification of the algebraic P1. And because of what we said right there, the Gaga remark on M, we know what the meromorphic functions, the global meromorphic functions on this infinitely branched tree are, right? It's just a function field of the algebraic P1. So M is the function field of P1. It's just rational functions over K. Okay, so from now on, when we talk of this CAN curve, the Berkovich curve, continue picturing this infinitely branched tree. So what happens in general is that the curve always has the structure of an infinitely branched graph, right? The difference here with this case is that the graph can in general contain loops. But at least locally, it's going to look something like this. So let's just look at this and keep in mind that everything I say can be generalized to those curves containing loops. And now let's maybe get back to local global principles. So part 3, I guess, but it's just a continuation of part 1. So let's say LGPs. Oh, and it occurs to me, okay, over Berkovich analytic curves. So it occurs to me that the title is Hasse principles, and I haven't defined a Hasse principle. But a Hasse principle is just a local global principle where the completions are discrete completions. Okay, so the completions are discrete. Right, so LGPs over Berkovich analytic curves. Let's get back to this statement and say a bit more. So the first one, the LGPMC, what is it telling us? Well, what it's telling us is that X has a rational point, which is a global meromorphic function. Remember, this was equal to F. If and only if X has meromorphic, well, rational points which are local somehow meromorphic functions. So you can already see there's one direction which is immediate, right? Because a global meromorphic function is always going to be local. So this direction, it's all good. What about the other one? That's where the difficulty lies. So this one, what are we saying when we assume this? Well, we have a curve. We said this is how we're drawing it, our favorite analytic curve. And we know that locally, our variety has rational points. So this means that I can cover the curve. I can even find a finite covering because the curve is compact anyway. So, right, I can find a covering. Let's call the elements U. So for any U, I'm going to have xm of U non-empty. Because when it's defined, these points are just defined on a neighborhood. These rational points of X are just defined on a neighborhood of the point of the curve. Right, so I've covered all of the curve. That's great. I've covered it with rational points of the variety, which are meromorphic functions. So the first reflex might be, well, we just have a bunch of meromorphic functions. Let's glue them. And that's going to give us a global meromorphic function. But we have absolutely no hypotheses on these local points that assure that we can do the gluing. We don't know that we have compatibility in the intersections, right? No reason for the rational points to not be wildly different on the intersections. So we can't glue directly. And what happens is that this is where, precisely where, we need the action of the group on the variety and where we need patching, right? So we get this direction by using the fact that G acts on X transitively plus patching. So I won't get into too much detail here, but what happens is essentially that due to these two things, we can refine this situation a bit and move these local rational points just enough in order to ensure that now we do have compatibility in the intersections. So we are in our ideal situation, and we'll just then glue meromorphic functions and get something here. Okay, so this is proved via patching. The second one, the LGP val, right here, is a consequence. It's actually equivalent, but it's a consequence due to the properties of Berkovich curves. So T3 goes up, T2 goes down, or let's say T1 goes down. Yes, of course. Because I haven't spoken of patching. I'm not sure I'll have the time, but it's to make sure that patching does work. This patching technique that one needs to move around the local solutions to get to something compatible on the intersections. But we're not seeing it here. It's really needed to prove this patching. which is mysterious for now because I haven't told you what it is. Anyway, so the second one, well, as it turns out, oh yeah, I should have maybe mentioned it up there, but, well, I'll mention it here instead. Before getting back to one remark, I said something about this being a reasonable local global principle, and this is due to the good properties of these fields, of the overfields MC. So these satisfy several good properties, amongst which they are Henselian valued fields. So they come naturally equipped with a rank 1 valuation. This is due to the structure of Berkovich curves. And as it turns out, it's Henselian with respect to this valuation. So this is going to be important for my second point when talking about LGP val, because as it turns out, there exists a bijection between the points of our curve, so of our infinitely branched tree or graph, and the valuations, or I'm going to call it VF, but it's exactly the valuations that you see appear here on the local global principle. So you have V over F, rank 1, non-trivial, and when restricted to K, you're either trivial or just VK. So you have this bijection, meaning the points of a Berkovich curve are just valuations of F. And moreover, it's if, say, to a point C, we've associated the valuation, let's call it VC, what happens is that when you complete F with respect to VC, it's exactly the same thing as completing this valued field MC with respect to its valuation, right? And so now this means that if I were to know that I have points over all of these completions, this is equivalent to knowing that I have points on the MC hats everywhere. And this, because we are talking about Henselian fields, by an approximation argument, is equivalent to having just MC points for any C in CAN. And this is how one proves the LGP val. So it's a consequence, it's in fact equivalent to the LGP MC. And right, I don't have a lot of time, but I do. So like I said, this all applies to quadratic forms because of the example there on my left. But by working a bit more on this, I just want to mention a result because I find it quite fun, is that if you take P different from 2 and Q over QPT, a quadratic form of dimension at least 9, so this means that you can write Q, of course you can write it diagonally, and the AI, so n is larger than 9, and of course the AI are not 0. So this is what the dimension means. Then Q equals 0 has a solution on QPT. So now we're talking directly about rational points. This was already known, first proven by Parimala and Suresh in 2009, circa 2009. Then HHK, Harbader, Harpen, and Krashen using this algebraic patching, also around 2009. And then I managed to slightly generalize it by this geometric patching on Berkovich curves. Right. Let's get back to the conjecture now. So we have the conjecture here. We're wondering about it. The first step already, let's interpret it directly on the Berkovich curve. So from now on, assume K is discretely valued. Let's define a subset of our curve CAN corresponding to the valuations that are of interest to us now, the discrete ones. So as disk is going to be the set of all of the points in my analytic curve, in my infinitely branched tree or graph up there, such that the corresponding valuation, so VC here, with respect to this bijection, is discrete. Now, this is a subset of CAN. It's a proper subset. It's never equal to CAN itself. It's never empty either. So, yeah, I can tell you a bit about the points that live in S-disk. So this is our favorite curve, CAN. So inside S-disk, we're going to have all of the branching points. Let's say yellow point is an element of S-disk. So all of the branching points, etc. Then, of course, you're also going to have all of the Zariski closed points, right? They also define discrete valuations on F. So that, we said, are, well, leaves, extremities of the tree. So we have plenty of these extremities in S-disk as well. But what does it mean? How big is this S-disk? Well, remark, S-disk is dense in CAN. Of course, this doesn't mean that we're done, because we can always have, not every point is going to be covered by neighborhoods of these points in S-disk. We can always have some isolated point X, which we can't put close enough to one of these points. So thanks to this subset, one can now reformulate the conjecture as follows. So let's say conjecture prime. So it's just a geometric, if you will, reformulation of CT PS. It states that X has MC rational points for all C in disk. So essentially we're saying we have local points, rational points on all of the discrete completions. This implies we have local points everywhere, local rational points of the variety everywhere. So this is what the conjecture becomes over the Berkovich curve. And, well, one can say something. Now, I think the conjecture is probably false in all generality. There are some cases, for instance, for G, if you take homogeneous varieties for G non-rational, where there have been counterexamples. There have even been counterexamples if K is not a p-adic field. So the question is, when does it start becoming false? What one can prove, what I managed to prove so far with this Berkovich approach is, okay, so I'll just say some of the cases that we get this way, and then, so this dates 21, 22, and then I'll explain a bit about the general setting. So true for 1 quadratic forms, so provided we work over, I don't know, a residue characteristic different from 2 or whatever, and then 2, it's true when G, so these are going to be some sort of flag varieties, when G is, it works for both special unitary and unitary groups. So why does it work for these two in particular? Like I said before, the cases that we know are obtained, of this conjecture, are obtained through case-by-case considerations. So what happens here is that I can show the conjecture to be true in a setting under certain hypotheses, which are some strong smoothness hypotheses on the variety X. And then, thanks to a theorem of Springer, which I'm going to hopefully mention soon, just to let you know which one it is, one can apply this general setting and recover both of these, so by using the same setting in a sort of uniform framework. Given the time, let me just give you a grossly oversimplified, I don't know, a bit of a heuristic idea for the proof in the case of quadratic forms.
So what's the proof G for quadratic forms?
SOQ. It's right there. The special orthogonal group associated. Here, I don't mention the varieties. It's some sort of flag varieties. It gets a bit technical. But here we have to work with Hermitian forms. And Hermitian forms also satisfy this kind of Springer type theorem which we need, which is why we get them here. So right, so let's look at the quadratic form case idea for part 1. So we're assuming now that quadratic forms, we take a quadratic form, we assume it has zeros over all of the discrete completions of f, right? So we have q over f. Let's denote by x. So we're working reciting characteristic different from 2. Let's assume we've diagonalized. This is our quadratic form. And we take x, the variety determined by q. And what is going to happen? Well, let's take, again, our favorite analytic curve. So, and let's start by isolating the bad reduction points of x. So let's say, is CAN, bad reduction points of x. So, of course, this is a finite set of points of Zariski closed points in the curve. And we said that they're contained in S disk, right? So Z is contained in S disk. And for these, we're all covered. We know by hypotheses that we have local solutions around the points. So, like I said, let's simplify things and assume that these Z are nicely grouped together. And let's say that we have only 2 U's. You have like a U1 and a U2. So everything that is in U1, union U2, we're all good. We know that we have locally points because this is true. So what remains unaccounted for are the points that are in the complement. So let me give this complement a name. It's going to be in violet, and I'm going to call it V. So we want to look at V now. So as it happens, you can choose your sets U1 and U2 in such a way that by a theorem of Bush, there exists a ring, a subring A in O of V, so in the ring of analytic functions on V, which is of course contained in MV, such that, well, already frac of A is just MV, so it's not too small, but also this is a complete regular local ring of dimension 2. Now, what does the Springer theorem say that I'm mentioning? Springer theorem, it states that if you take K, big K, to be a complete discretely valued field, and you take Q over K, let's say T is a uniformizer, you can write Q over K, Q can be written as some Q1, some T Q2, with Q1, Q2 defined over, so you can write them diagonally if you want, and I want the constant, the coefficient, to be an OK star. And then what the Springer theorem says is that Q equals 0 has a solution if and only if over K, if and only if Q1 or Q2 have solutions over the residue field. So you can't take them over the residue field because now they're defined over OK stars, so if you quotient, you're not going to lose anything. Right, so how does this help us? Well, because of the fact that we isolated the bad reduction points, I can choose alpha, beta generators of the maximal ideal of the ring A such that Q is isomorphic to Q1 plus alpha Q2 plus, let's factorize a beta, Q3 some alpha Q4, where the Qi are defined over A star. And now I can look at the following. So the ring A, and I'm going to localize it beta and maybe also complete. This is going to be now discretely valued. F is going to be contained in its frac, and the Qi's are all defined over A beta star. So I can use Springer's theorem to already reduce to, so Springer, here beta is a uniformizer. We know that Q is Q equals 0 has a solution here by hypothesis. So we can reduce by the Springer theorem to Q1 plus alpha Q2 equals 0, or Q3 plus alpha Q4 being 0 has a solution over, so the residue field of this, which is just the frac of another discretely valued ring, which is also discretely valued. And again, so now we know, let's say it's this one. We're saying this has a solution over this discretely valued field, okay? If we say that, well, plus the Qi are again defined over frac over, you can just assume A over beta star, because don't forget they were defined over A star. And this is just going to give you that one of these, let's say Q1, has a solution over A over alpha beta. So A over its maximal ideal, and then you apply Hensel. Q1 equals 0 has a solution over A, which is in MV. So Q equals 0 has 1. So we're accounting for also all of the points here, and we're done because we have managed to get all of the points. And it works kind of similarly also in the second case, where what happens is that you have this kind of Springer type theorem for Hermitian forms. Right, so I'm done, and thank you.
Thank you very much for a lovely talk. Are there any questions? Arno, I come and run to you. No, I'm not allowed to do this.
Thanks. Thank you. I'm just wondering, because you said HHK use algebraic patching, I thought they would strongly disagree with that statement. I mean,
which one?
that they use algebraic patching because don't
But they
say
call it
use
algebraic
field
patching.
which is completely
Okay, fine, they
different
call it
from
field
algebraic
patching. I'm not sure that they would disagree.
But you're not, okay, you're not making a political statement.
I'm not at all. I don't mean it in a bad way at all. I mean, it's a really phenomenal kind of patching. It's not, for me, it's not a political at all. It's just an interpretation that I have, which is by no means to downplay the importance at all.
Okay, well, thank you. Thank you.
So I'm afraid all other questions, I mean, unless someone has a very, very urgent question, but should wait until after lunch because we all need to run to lunch now. And then we meet at 4 p.m. here to have coffee again. Thank you very much.